It's time for another amazing chemistry video with Mr. Stapleton, proudly sponsored by Farmers Union Nice Coffee.
Hi guys, welcome to today's video. This is going to be all about extraction of metals. Okay, so when we're talking about extraction of metals, we're using this within the electrolysis topic, and what in particular we're going to be looking at is extracting metals from their ores. Now, the first thing you need to understand when we're looking at extraction of metals is you need to be able to identify what method we would use to extract the metal from its ore. Now, an ore is how the metal is combined within the surface of the earth. So an example is aluminium is found combined with oxygen because it's quite a reactive metal, so it's aluminium oxide, which is bauxite. Iron is found as hematite, which is Fe2O3. Zinc is found as zinc blende, which is ZnS. Okay, so you often find the metals combined with other elements in the surface of the earth, and so you need to know how we're going to extract that metal out of that ore. And you do that through electrolysis generally, or reduction, but electrolysis is quite common. Now, depending upon the reactivity of the metal will determine what method you use. As your reactivity decreases, the method that you use becomes a bit more simple and a bit cheaper as well. So if you have very, very reactive metals, okay, so if the reactivity is really high, okay, what you're going to do is you're going to use electrolysis of the molten solution. So you're going to take your ore or your mineral, like your aluminium oxide, Al2O3, and you're going to heat it up so that it melts, and then you're going to pass electric current through it. So it's electrolysis of the molten salt, and you do that to make sure that the metal is produced at the cathode, okay, in preference to anything else. If you've got a metal which is more in the intermediate reactivity, so zinc's an example, iron's another example, there's two methods you can use. This time, because it's not as reactive, you're not trying to force it to gain electrons as much as you are with a highly reactive metal, and so you can use the aqueous solution, or you can use carbon reduction. So if you've got intermediate, you can use one of these two. Okay, so aqueous electrolysis means just simply dissolving your mineral up in water, passing electric current through it. Carbon reduction means literally putting carbon or coke, which is raw carbon, into a blast furnace, and you use that to undergo your reduction to produce your metal at the which is what you need. So that's, for example, used for the production of iron from iron ore. If you get down to metals which are really low in reactivity, okay, then you can use just heating. So good examples are things like gold, silver, mercury. They're very unreactive metals, and so all you've got to do is basically heat them to get them out of their the ore that they're in, and you get the pure metal out of it. What we're going to be really focusing on is the electrolysis side of it. So we're going to be looking at both the molten electrolysis and the aqueous electrolysis here. So I'm going to start off with the molten electrolysis, and I'm going to use an example of, say, sodium chloride. Let's say you wanted to get the pure sodium out of a solution of sodium chloride. Now, if you pass an electric current through an aqueous solution of sodium chloride, what you've got in that aqueous solution is sodium chloride, but you've also got water. Now, sodium is a highly reactive metal. What you are trying to do is this. You're trying to get sodium ions to pick up an electron to form sodium. Alright, that's what we're trying to get. Now, metals generally by definition want to give away electrons. They don't want to accept them. Okay, they're quite happy to give away electrons. So forcing a sodium to pick up an electron is not favourable. What it would much rather do is pick up, get the water, the hydrogen in the water. Hydrogen is not a metal. It would much prefer to get that hydrogen to pick up an electron to form hydrogen gas. So if you do an electrolysis of an aqueous solution, the hydrogen gas would be formed in preference to the sodium because it's much more energetically favourable. Now, this reaction, which is reduction, which is a gain of electrons, can only happen at the cathode. Okay, because we're doing electrolysis of the molten salt, okay, the only other thing we've got within here, we've got sodium ions, which we've just done at the cathode, and the other thing we've got are chlorine ions. Okay, so those chlorine ions must be involved in oxidation at the anode. So our chlorine ions here are going to form chlorine gas, and they're going to give up electrons and those electrons are what the sodium picks up to form solid sodium metal. So you force the production of your metal at the cathode simply by using the molten salt. So it doesn't really matter which reactive metal you're using, okay? You have to use the molten salt, so you heat it up. A lot of obviously cost involved with that, with firstly getting it to that molten state, because they're ionic substances, they have very high melting points. And then there's a cost involved with the electrolysis of it, all right? So all in all, this is a very expensive process to get the metal out of the ore. However, there's no other way we can do it, because as soon as you go to the aqueous electrolysis, you get hydrogen formed in preference. Okay? So that's electrolysis with a molten one. I'm just going to show you an electrolysis of an aqueous solution.
Hang on, so are you saying that if you have a highly reactive metal, you can only use molten electrolysis?
That's correct. All right. If it's highly reactive, you can only use molten electrolysis. But if it's intermediate, you can use aqueous. Thank you for that very good question, Mr. Lacornia.
No worries, anytime.
So what we will focus on is aqueous electrolysis, okay? And the aqueous electrolysis is where you have a less reactive metal, and it doesn't matter if the metal picks up electrons because it's not as reactive. So I'm going to look at a very common one that we use is zinc. All right, zinc is commonly found as zinc sulfide. All right, we do a conversion of that to get over to zinc sulfate, which is what we use for electrolysis. Okay. Now in this case, in this solution, we have zinc ions, we have sulfate ions, and we have water. Okay, because we're doing this time the aqueous electrolysis. Now because we've got water, we can now get electrolysis happening of this. When you electrolyze water or pass an electric current through it, you get two things. You either get hydrogen gas or you can get oxygen gas, okay? So, because the zinc here is of an intermediate reactivity, again at the cathode, remember that's one of the rules, that the metal is always produced at the cathode. Zinc picks up electrons and forms a solid zinc. So like we had for the sodium in the last one, the metal is formed at the cathode. At the anode here, there's a number of different options we could have, all right? One of the reasons we use sulfate is that it doesn't react when we're going through electrolysis very often. It's very stable, and so quite often what we'll get for the product at the anode is something to do with the water if it's an aqueous solution. So in this one here, if we've got hydrogen, that H plus from the water would need to pick up, so that comes from H plus, that comes from O2 minus, that hydrogen would have to pick up electrons to form H2. Gaining electrons would be a reduction at the cathode. We've already got a cathode reaction here. Remember, that's why I said that if you do a very reactive metal in an aqueous solution, this will take preference because that H plus will pick up electrons. So what we're having over here is we've got the water, okay, which is going to form oxygen gas. We can just do a half there, okay. It's going to form hydrogen ions and electrons. So we're going to get oxidation at the anode, which we always get. That H plus will lower the pH at that electrode, which you could test for with like universal indicator or litmus paper, okay? And this is what we're getting. So when we've got an intermediate reactivity, you can do this aqueous electrolysis because you will actually get the product you want at the cathode instead of the hydrogen. So there's a couple of videos you probably want to have a look at. Well, in conjunction with this one, you probably want to look at the video on electrolysis because I go through some of the different factors that affect electrolysis. And as always, if you've got any questions, just ask. I mean, Mr. Lacornia asked a great question. You can too. Thanks, guys.